welcome in the time domain. The story I want to talk about today started actually when the first MIRI paper came out, and people started speculating, the authors, what could be the reason that the newly measured MIRI flux or MIRI spectrum is so different from the old Spitzer spectrum. Actually, there were already similar results in the literature earlier. I just show here from Agnes Kospal in 2012. She showed that similar big differences were present between the ISO and the Spitzer observations. But anyway, this new discrepancy between the MIRI and the Spitzer, it kept busy at least part of the MIRI community, thinking whether it was a calibration issue or the inner disk are more variable or more dynamic, everything. Mr. Gajdos here in the first row turned it in the opposite direction. He used these differences to interpret and learn about this structure. So I just saw that it's an interesting topic. It's worth to investigate. So as a first step, we downloaded all publicly available James Webb MIRI spectra of young stellar objects from the cycle 1, compared them with the Spitzer spectra. These are just 3 examples. And what we found that really a lot of objects show noticeable differences. Actually, we measured some 80% of the young stars showed different Spitzer and MIRI spectra. And one can interpret it that during 15 years, which is the difference between the 2 instruments, really big changes can happen somewhere in the 10 micro range. I think it's an important contribution of James Webb to the star formation field. Also, to continue a little bit this investigation, we selected a sample of young stars, some 10 classes. This is the source list, and initiated a monitoring campaign. The idea was that we take as complete spectral energy distribution in the infrared as possible simultaneously. It's very important to have at the same time. And we used a lot of instruments, a lot of proposals, accepted or rejected, and the main aims were to characterize the mid-infrared variability, to determine the physical origin, why we see different fluxes and different spectra, and whether we could learn from it something about the inner disk structure and maybe even dynamics. So these are the results, at least for 4 examples out of these 10. But you see that these are the ranges where the Spitzer and the MIRI, Spitzer is always gray, MIRI is the red one, are so different that we knew before because the sources were selected on that. But also in other parts, you see a lot of variability. So I would like to call your attention to this part. You would see in all sources the same. This is the old Spitzer spectrum. And the new MIRI spectrum, the red one, they define a certain range. And but one can say that, okay, the source changed so much, faded so much from here to here in 15 years. But we had new observations with the VLTI visitor instrument, the green ones. And what we see that we can feel the same range, which was defined in 15 years by the 2 instruments. Our observations feel the same range in just about 6 weeks. So the time scale is not 15 years, it's just a few weeks, which causes this variability. It already excludes one possible physical reason, because originally one would think that, well, why do we have changes here in the 10 micro region? Because the part of the disk which is emitting at this wavelengths, usually a few astronomical units from the star, changed. Maybe the flaring changed, the disk became more puffed up, you have more emitting surface. No, this is not the case. In 6 weeks, you cannot make it. So the only possibility to explain it, that it has to be illuminated, and the illumination of this region has to change. You cannot assume physical changes in the structure. So let's see, let's investigate the case of this S198. You see a lot of variability here. Obviously, this comes from the star. So if we say that it must be the illumination of the disk which causes this MIRI-Spitzer discrepancy, then I first question whether the star is variable or not. We checked for that. we use the method so-called veiling. This is the spectrum of our spectra, because we have IRTF spectra here, and check the depth of a certain absorption line and compare it with a non-accreting other similar spectral type source. And so that our measurements are much shallower, our line shallower, which means that the source is accreting. And one can measure this how much it's accreting, and we could see that indeed this star is a strong accretor, and the accretion rate is changing as any good accretion rate should do. So it is variable. So far so good. Actually, we have an explanation. We have a star which is changing due to accretion, changing its brightness. It illuminates the disk part where the 10 micron region comes, and it explains the Spitzer and the Miri. But the star can change for another reason also. This is a light curve, and we see here really deep minima here. What could it be? Certainly are not accretion events. These are much more circumstellar extinction. So some dust clouds just pass in front of the star, which is interesting because according to ALMA, the inclination is about intermediate, 47 degrees. So this dust must be really just above, far above the disk plane. And it must be very close to the star because of the quick variability. So finally, one can assume that what we see, this light curve and the quick eclipses, it comes from the inner edge, from the inner rim of the disk, around 0.1 AU or something like that. Actually, Neil Turner published some years ago a model which would lift up some dust clouds temporarily into the disk atmosphere. So we imagine something like this. Okay, if we have a star which is variable because of variable accretion, now we know that there is dust material, there is a dust wall around it. This dust, which is variable anyway, this dust must also emit, since it absorbs the starlight, so we should see its emission. Can we see it? Yes, we can. This is one of our spectrum, and the green is the photosphere of the star, corrected for accretion, for extinction, for all these things, and we still see an excess here. Fitting this excess, it's possible to fit this excess with a black body, in this case of about 1000 K, and this is obviously some warm material close to the star. What else could it be than the emission of the inner rim? So we see it, and if we measure it for the different epochs when we have, we see that this inner disk emission is variable. Its temperature is pretty constant, but the emitting area changes by something like 40%. Anyway, the temperature is lower than 1500 K, so probably it's not at the sublimation radius, it's a bit more distance. So, of course, one would be happy to say that when the star is brighter due to accretion, then you see more emission from this inner rim. That would be a perfect world. In the reality, we don't really see this correlation yet. We have to massage the data a little bit more. So what is our picture of this star then? These are all observations, all multi-epoch observations. So what we see, that's the strong accretion variability of the star. If we subtract it from the full spectrum and fit the inner disk part, this is the green one, this is a single temperature black body, and you see that it is variable, but it's not really correlating with the star, that's my feeling. We have still a remaining part, the outer part, which is the material behind the inner wall. Interestingly, anyway, I have to note that up to something like 8 or 9 micron, in this case, this inner rim dominates the emission. So if you see in your James Webb spectra any variability below 8 or 9 micron, that its slope changes, this is not the outer part, this is just the inner wall Planck curve. So we have a silicate feature, which is almost constant, And we have another part which is not, which seems to be actually correlating with the stellar radiation. It's a sample of 2 points in astrostatistics, and we don't see any shadowing. Probably the outer material we have to place somewhere above this inner rim to get directly illuminated by the star. And we have a constraint on the time scale that in 6 months we have a change in the rim surface by about 40%. Another case that I wanted to show, that HT loop, where interestingly, the star doesn't change at all. So what's happening? Still we have a strong mid-infrared variability with a constant star. The star is indeed constant. This is a long-term light curve, and it changes on a very, very little. So still, the mid-infrared part, we have an axis above the constant star. We can fit it with the same black body, whose temperature is now close to the sublimation temperature. And what we found, that at different epochs, which are within a few weeks or months, we have a huge change in the emitting area. It's 87% or something like this in this case. So what's our picture? We have a non-variable star. We have a highly variable inner disk. You see how these green lines change. And we have also the other part, which is highly variable. One cannot imagine any other reason to cause this outer part variability than somehow shadowing, because the star is constant. So the only possibility that when this rim is higher, then it blocks the light to the outer part, so this should be lower. We try to see it from the 3 points, because we have only 2 Spitzer and 1 Miri data. Of course, it does not work, but hopefully it cannot be anything else than shadowing. And here we say that in 6 months we have a lot of change in the inner rim surface. And this is my summary page, which tells that we could get a lot of useful information as an input to the radiative transfer models from variability. We have a picture of the inner disk actually, and also give some constraints on the time scales. And for the future, we will finish it with the other object. Initiate multi-epoch interferometric studies. I think it will be very important. And the last point is a plea to you that when you observe with Miri, please try to get simultaneous infrared observations, because it makes your life so much easier. Thank you very much.
Nuria Calvet, Michigan. It seemed to me the first star that you showed, the one that varied a lot, that when it got fainter, got redder. So if that's the case, maybe you could get some information about the grain, the dust that is actually producing that variability, assuming that it's like a extinction events.
Yeah, maybe here it's really a combination of an extinction and a variable star, so we have to try to separate the two. That's the challenge.
So, Peter, on the SZ 98, what does the NEOWISE data show? Does that also give you some indication of the variability?
Yes.
And
these are the NEOWISE data, here in the L and the M, the W1, W2 bands. So it's completely consistent with all other observations this year.
And so do you have any sort of fortuitous timing of the observations that you can rule in or out the seesaw?
No.
Or is it just the fact that
it's really a pity that this objects change very quickly, and if you don't have very close time, then you cannot really make a LCD. So that's why I think one should really get dedicated spectral energy distributions.
And NEOWISE was terminated at the end of life.
NEOWISE terminated anyway. It's Phoenix, maybe.
I have a question. Maybe I missed it. Is it clear why the silicate feature isn't varying?
I'm sorry?
Is it clear why the silicate feature isn't changing?
The silicate feature, interesting in the first case, which was so variable, when I just subtracted a continuum and just left the silicate feature, this is remarkably constant. And the shape is also very similar, so it did not change. I don't think there would be any big change here. In the other case, that was more change.
Thank you. Let's thank Peter again.